Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the case in which there is a cylindrical container which is filled with some liquid and we are rotating the liquid along with the container with an angular velocity of omega about the central axis. So in the practical scenario, in such a case, you could imagine that the free surface of the liquid will be like a curve. It would depress from the bottom and it would elevate from the edges and it would make a curve. Let us now discuss that which curve is this and what is the pressure at any point inside the liquid. So first of all, let us see that why this happens, why the liquid free surface changes its shape. So to understand this, let us consider a point this, and let us say that the coordinates of this point is x comma y. It clearly means that the distance of this point from the axis of rotation is x, and hence we can say that the centrifugal force acting on this point, or we can say that some particle is situated at this point, so centrifugal force acting on that particle will be mx omega square, and the mg acting on this particle will be in the downward direction. This is mg, and the net force acting on the particle will be like that, F net. Okay, so if we draw a tangent at this position, let us draw a tangent, and let us see that if this angle is theta and this angle is 90 minus theta and this angle is theta, so we can say that the tan theta, first of all let us do one thing. Yeah, so we can say that the tan theta at this position will be equal to this vector upon this vector. This is perpendicular vector, which is mx omega square upon base vector is mg. So tan theta will be equal to x omega square by g. And we also know that tan theta is the slope to the curve. This is dy by dx and it is x omega square by g. So dy will be equal to x omega square by g into dx. Integrating both the sides, limit is from 0 to y, and here the limit will be from 0 to x. And what is y? Y is in fact this height. This height is y. This height. Okay, this is y. So y will be equal to x square omega square by 2g. This is the value of y. Okay, now if in a different case, if we have to write down the pressure of this liquid in the container, so let us see that at some point here the coordinates of this point is minus x comma y. So let us name this point as A, and let us name this point as B, and let us name a point C which is just below A and B. This is C. And let us name a point D which is just in the level of C, and let us name this point as E. Now first of all, we know that pressure at A will be equal to P naught, and pressure at B will be equal to P naught which is PA, or we can write it as PA, but let us directly put the value of PA as P naught. P naught plus this height is Y. So this is y rho g. Now it is very important to note that when we are moving from A to B, the pressure will vary only due to the gravitational force, and it would not vary due to the centrifugal force, because when we are moving from A to B, we are moving on the y-axis, which is parallel to the axis of rotation. And due to this fact, the distance, we can say that the distance of these points A and B from the axis of rotation is constant. So centrifugal force acting on these particles will be constant. So we can say that PB will be equal to P naught plus y rho g, where y, the value of y is x square omega square by 2g. So first of all, let us, yeah. So this is x square omega square by 2 into rho. G is cancelled out. So this is PB. And again at C we can write it as PB plus, if this height is, let's suppose, small h, or let's suppose this height is y naught. So it would be y naught rho g. Now the pressure at E is obviously P naught, because atmospheric pressure will be there at this position, and pressure at D will be equal to PE plus y naught rho g. Now if you are wondering, now let us first of all write down the value of PE, which is P naught plus y naught rho g. Now if you are wondering that according to Pascal laws the pressure at C and D should be equal, this is absolutely incorrect. Pressure at C and D will not be equal, because C and D are not lying on a equipressure line. So if let's suppose that this point is C and a point D is in same level of C, so you can see that these are not lying on a equipressure line, and the equipressure lines will be this, like this. These are the lines which are parallel to the free surface. So equipressure lines are this. So C and D will not have equal pressure, and they should also not have the equal pressure because they are not lying on a equipressure line. So some point which is at this position will be having the same pressure as that of C. Okay, now this is the pressure, and if we discuss the shape of the surface, then we can say that y is proportional to x square, then this shape will be parabola. But obviously this is a line. Parabola is two-dimensional figure. So this 2-dimensional figure is a parabola, but in 3D, 3-dimensional figure is paraboloid. This is paraboloid. So the free surface of the liquid will attain a shape which is called as paraboloid, and I think that you must have studied paraboloid in mathematics. So this is the scenario. Now let us analyze this situation again in different manner. Let us use the next page. So first of all, yes. So in this case, you can see that that initial water level was H, and let us suppose that H is this. This is H. H was the water level in the container when the container was not rotating. So this was H initially. Now when we started to rotate the container about the central axis, then the central point of the liquid surface depressed by a distance of x2 from the original level, and the extreme point of the liquid surface, which is in contact with the container, elevates by a distance of x1 from the original level. Now we have to establish the relationship between x1 and x2, and also we have to find out their values. Now first of all, let us write down the value of h. So we have, if this is origin, we have already derived an expression of y where we can see that y is x square omega square by 2g. So y is x square omega square by 2g. Now if we wish to find out the value of h, we can substitute the value of x as r in this equation. So y will be h when x will be r. So this is h. Now I'm telling you that if this is a cylinder, let us see, if this is a cylinder, then we know that the volume of the cylinder, V cylinder, is equal to pi r square h, where this is h. Now if we draw a paraboloid like that, then the volume of paraboloid, which is the volume enclosed in the paraboloid surface, so this volume of paraboloid will be equal to half of the volume of enclosing cylinder. Therefore it would be equal to, if this is h, then it would be equal to pi r square h, where r is the radius. So you should remember this thing. Now we can say that if you just have to focus on this cylinder, we can say that when the container was at rest, this complete liquid cylinder was like that. Okay, and when container started to rotate, the cylinder of liquid, which is this one, is still the same, because no liquid is displaced from the cylinder. But we can say that the liquid which was initially inside this cylinder gets adjusted into this part. I am shading the part, this part. So the liquid which was initially inside this cylinder is the liquid displaced. So let us find out the volume of liquid displaced. So volume of liquid displaced is equal to this volume, and this volume is x2 into pi r square. So it would be x2 into pi r square. And we can say that this volume is adjusted in this part. Okay. And the volume of this part will be volume of this cylinder minus volume of paraboloid. Okay. So this will be volume of the bigger cylinder, this cylinder. The volume of this cylinder will be pi r square h. Pi r square h minus the volume of paraboloid will be half. So it would be pi r square h by 2. So x2 into pi r square will be equal to pi r square h by 2, and hence you can see that x2 will be h by 2. And therefore we can see that x1 plus x2 is h. So x1 plus x2 is h, and hence x1 will also be equal to h by 2. And the value of h is this one, r square omega square by 2g. So we can say that x1 will be equal to x2 is equal to r square omega square by 4g, because x1 x2 are h by 2. So this is the analysis of the liquid which is being rotated in this cylinder. And let us discuss a numerical to clearly understand the situation in detail. So you can see that there is a cylindrical vessel. Let us draw this vessel. The radius, in fact the diameter of the vessel is this. So the radius of the vessel is 0.15 meter. And the height, total height of this cylinder h is equal to 0.6 meters. And the density of liquid filled is 0.8 into, this is specific gravity, so 0.8 gram per cc. And this cylinder is rotated about this axis. So initially the liquid was at 2/3 height. So if this is h naught, so h naught is equal to 2 by 3 of h. So it would be 0.4. So we would be deriving all the solutions in terms of variables, and at the last time we would be substituting these values. So we have to find out the omega when liquid will start to spill out of the vessel. So let us see the first situation. When the liquid will start to spill out, the parabola or the surface would be like that. Okay, and this would be h by 2. So we can say that this h by 2 will be equal to the remaining height, and the remaining height is 0.6 minus 0.4, which is 0.2. And h will be equal to 0.4. and we have already derived the value of h as this one, r square omega square by 2g, because it is h by 2, we are talking about h, so it would be r square omega square by 2g. So this will be equal to r square omega square by 2g, and this omega 1 will be equal to 0.4 into 2g is 40 and r is 0.15 whole square, and this is omega 1 square. So we are not calculating the value of omega 1 square to be precise, and we are just leaving this like that only because we would not waste the time in calculations. In the second case, we have to find out the omega when the base of the vessel is visible. So let us use a new page. Let us draw the situation. And let us see that when the base of the vessel is visible, then the surface would be like that. This would be the surface. Okay, and in this case, we can say that the omega is omega 2 and this height is h. Now again h is r square omega square by 2g. So h is r square omega 2 square by 2g, and this h will be equal to the height of container, and this height was 0.6. So this h will be 0.6. So omega 2 square will be 0.6 into 2g, which is 20, and this would be, sorry, it would be 20 only. Okay, and yeah, sorry. So this is 20 and divided by r square is 0.15 whole square. Okay, and in the third case, we have to find out the percentage of liquid which is left in the vessel for the second case. So in the second case, if we find out the liquid volume which is left in the vessel, V left. So V left over will be equal to volume of this cylinder minus volume of paraboloid, which would be half of the volume of cylinder, which is pi r square capital H by 2. This is the volume of liquid left in the cylinder, in the container in this case. And the original volume V naught was equal to this this h naught, which is 2h by 3. So 2h by 3 into pi r square. So original volume was 2h by 3 into pi r square. So the percentage of volume left in the container will be volume left upon total initial volume into 100. So volume left is pi r square h by 2. Initial volume was 2 pi r square h by 3 into 100. So you can see that this pi r square h is cancelled and it would be 3 by 4 into 100. So it is 75%. So 75% volume is left in the container in this case. So this was the complete analysis of rotating container, and in the next video we would be discussing the case in which we would rotate the U tube about one of its arm. Thank you.